We're going to start a new section today, section 8.4. As you can see there, it's on the multiplication principle, and we'll get into permutations and combinations. So our objective there is to look at permutations, combinations, figure out what they are, and then solve a couple problems involving both the permutations and combinations. So first thing, we're going to get into an example of the counting principle here that you'll see in a second. So we have Big Dave's, you have the choice of ham, turkey, or roast beef on different types of bread, rye or white, served with juice, milk, or tea. So it says make a tree diagram to determine how many possible lunch combinations there are. So let's start with the type of meat that we have. We have ham, we have turkey, and then we have roast beef. From each type of meat, we then have a type of bread. We have rye or white for here, and one more time, rye or white. Lastly, we have the type of drink. So from each of these, from the rye and white, move these here, we have juice, milk, or tea. Juice, milk, or tea. Same thing here, juice, milk, or tea. Juice, milk, or tea. So obviously this is what we call the tree diagram. The juice, milk, or tea here, and lastly juice, milk, or tea. So let's call it juice, milk, tea at the end there. So one possibility of a lunch combination is ham on rye with juice. We also have ham on rye with milk, ham on rye with tea, and so on. So if we wanted how many lunch combinations, we would add up all of these. So there are 3 here, 3 more here, that's 6, 3 more is 12, 3 more, and 3 more is 18 total. So 18 total possibilities here. That's what a tree diagram looks like. But that's what we call the fundamental counting principle, the multiplication rule, and much easier done if you have n sub 1 outcomes for one operation and n sub 2 outcomes for another operation, and there are n sub 1 times n sub 2 outcomes together. The key here is that you are multiplying those two outcomes, those possible outcomes together to get your possibility. So let's go back to this real quick. Without doing this tree diagram, we have three possibilities of meat. We have 2 possibilities of bread, and we have 3 possibilities of drinks. And then if we are multiplying these all together, we have 2 times 3 times 2 times 3 gives us the 18 that we came up with a second ago. So another example of those, how many outcomes if you flip a coin and roll a die. If you flip a coin, your possible outcomes are heads or tails. So you have 2. When you roll a die, you have 6 outcomes. So 2 times 6, you have 12 possible outcomes. If you roll 2 dice, you have 6 outcomes with the first, times 6 outcomes with the second, for a total of 36 outcomes for 2 dice. Something factorial. So factorial is where you're going to take some number, n. So n factorial is denoted by that exclamation point. It's the product of the first n natural numbers. What that means, if I have n factorial, it's going to be n times n minus 1 times n minus 2 times n minus 3, all the way down until I get to times 2 times 1. So, for example, let's look at a number now. If I had 5 factorial, that's going to be the same as 5 times 4 times 3 times 2 times 1. Notice here, 1 factorial is 1, that's easy enough. 0 factorial is also just 1. A couple examples of this. Now, in your calculator, you have a button on this. In your graphing calculator, actually on the scientific as well, but in the graphing calculator, if you go to Math, and then scroll to the right to PRB, and then in PRB, you'll see at number 4, there's the exclamation point. So that's where you get it on your graphing calculator, and again, similar on your scientific. But 6 factorial, again, I'm just using my graphing calculator here. 6 factorial is 720. Again, that is 6 times 5 times 4 times 3 times 2 times 1. For something like number 5, where we have 6 factorial over 5 factorial, so I'm going to write this out, and I'll show you why here in a second. So you could plug that into your calculator, or you can think of it this way. 6 times 5 times 4 times 3 times 2 times 1 all over 5 times 4 times 3 times 2 times 1. And you'll notice what happens here with all of this is going to cancel out, so you're left with just 6. So recognize now number 6, this sixth example, that 9 factorial over 6 factorial, from 6 on down is going to cancel out, so I'm left with 9 times 8 times 7, which is 504. Same premise on number 7, everything from 198 down is going to cancel out, so I'm left with 200 times 199, and 200 times 199 is 39,800. So if we get into some more of these types of problems, how many license plates are possible if each consists of 5 letters. So 5 letters, I have 26 times 26 times 26 times 26 times 26. Again, multiply those out. There's 26 possibilities for each of the 5 spots. I take that, or just 26 to the 5th power, obviously. You get 11,881,376. 5 letters but no repeats. So I still have the 5 blanks for the license plate, but now I have 26 letters, 25 letters, 24, 23, and 22. And that gives me the 7,893,600. 3 letters followed by 2 numbers, not saying anything about the repeats. So let's say these are all letters. There are 26 possibilities, 26 possibilities, 26 possibilities. 2 numbers, there are 10 digits, 1 through 9, including 0, times 10 times 10. So that gives me 1,757,600 possibilities for, excuse me, for 3 letters followed by 2 numbers. That gets us into what we call a permutation. So a group of objects or people or anything are arranged in order, arranged in a certain order. The key there is arranged. Keyword is arranged. Order matters for this. There's our formula, n factorial over n minus r factorial. N is the total number. R is how many you are arranging. So n is the total. R is how many you are arranging in a certain order. So let's look at an example real quick. If you line up 30 people in a line for tickets, you have 30. You're lining all 30 up. So I'm going to take 30 factorial over 30 minus 30 factorial. So again, I'm lining every single one of them up. This ends up being just 30 factorial. And if I take 30 factorial, give me 1 second here, I get a very large number, 2.65 times 10 to the 32nd. So there are that many ways to line people up, which is obviously a bunch. Arrange 8 books on a shelf. Again, I'm taking 8 as my total number of books. I am arranging all 8. 8 minus 8 factorial. So this is 8 factorial over 0 factorial, which is just 8 factorial over 1. The same thing we did up here, which is just 8 factorial. So 8 factorial ends up being 40,320. How many ways can you choose the president, vice president, and treasurer from a class of 10? So again, order matters here. The president is in a different position than the vice president, who's in a different position than the treasurer. So I have 10 total, and I am taking 3 of those 10. So it's going to be 10 minus 3 factorial, which is 10 factorial over 7 factorial, which, again, everything from 7 down is going to cross off, so I'm left with 10 times 9 times 8. And that ends up being 720 different ways you can choose a president, vice president, and treasurer from that class of 10. So looking back at 9b, it says how many of those books on your reading list for English class. You must read 3 of them. How many ways can you complete that assignment? It doesn't matter which way which books you read, as long as you read 3 of them. This is what we get into what we call a combination. So there's what a combination is: an arrangement or selection of objects in which order is not important. So permutation, order matters. Combination, order does not matter. Again, it's written many different ways. N choose R is how it's talked about. You can see here n factorial over r factorial times n minus r factorial. So similar in nature by all means. So a committee has 3 people on it, or how many committees of 3 people can be created from a group of 10. Here I just want the committee, the order does not matter. So n is, I have 10 total, so 10 factorial over r factorial, 3 factorial, times 10 minus r factorial. So this is 10 factorial over 3 factorial times 7 factorial. And again, 10 factorial all the way is going to cancel out, so I'm left with, I'm sorry, all the way from 7 down is going to cancel out, so I'm left with 10 times 9 times 8 all over 3 times 2. So 10 times 9 times 8 ends up being the 720 from earlier over 6, and 720 divided by 6 is just the 120. So 120 ways for 120 committees of 3 people that can be created. How many different 5-card hands can be dealt? There are 52 total cards, so 52 factorial. We're looking for 5 of them. Doesn't matter which 5. 5 factorial times 52 minus 5 factorial. I'll let you work that out. We'll deal more with. We'll look at more of this closely as we get into this more next week.